It goes without saying that most people would rather live in a world without war. But humanity as a whole is not guided by a common will and hardly works for a common goal. Decisions are made and actions are taken by individual actors. These actors can be people, groups, companies, governments, and the list goes on. They all act according to the goals they pursue, and for themselves, that is. So is it any wonder that everyone thinks that he or she is doing the reasonable thing, while the actions of humanity as a whole seem highly unreasonable or even suicidal? So next time you hear someone say, "Why are we so stupid?" ask them what they mean by we, and ask for examples when the whole of humanity has ever acted as one entity with one will and one goal. Unfortunately, disagreement and conflict seem to be part of the human condition. In this video series we cannot change that. But hey, at least a few 100,000 people from all around the world will come together here, because they have at least been able to agree on one thing. Objects that have once been made with the highest possible quality and durability in mind should not go to waste. They should serve for the longest possible time, independent of whether or not the initial reasons of their conception might or might not have been misguided. Me working on military items in these videos is not an endorsement of the human tendency towards violence, but an attempt to make the best of what was given to us by generations past and find new meaning where others will only see the pointlessness of bygone conflicts. What I have here are gasoline-powered electric generators that were built in West Germany during the Cold War. To be more precise, they were made in the 50s and 60s, and since these are two-stroke engines, oil has to be added to the gasoline. In this case, it's a 1:25 two-stroke mixture. The engines were all built by Fichtel und Sachs in Schweinfurt. F&S, often also just called Sachs, became big by producing ball bearings, but also specialized in the development and manufacturing of small combustion engines used in light motorcycles, bicycles, farming equipment, chainsaws. They even made Wankel engines, and there also were chainsaws with Wankel engines. But in today's video, we're going to encounter engines that are less exotic than that. These workhorses of the Sachs line of products are the stationary motors known as Stamos here in Germany. A while ago I got my hands on 6 of these small generators here that were stored in a now decommissioned military depot. In fact, this tag here must have been attached to the generator for at least 44 years, because that depot was closed in 1978. I must assume that that was also the last time that the engine was started and that the generator was tested. They were built in 1957, and here's a video that a viewer from Belgium sent me a while ago. It shows what these generators were originally built for, powering vacuum tube based radio transceivers that were used by different NATO forces at that time. But what about the generators I have? Do they work? And what are we going to do with them? Before we get started though, I also wanted to mention that I bought this bigger generator here as well, and its repair will be the centerpiece of this video once we have worked on the smaller units, but more about that in a few minutes. After inserting some two-stroke mixture into the tank, I will now try to start the engine. So far nothing happens though. Opening the choke didn't help as well, by the way. So I'm checking the old spark plug and it looks rather crusty, so let's insert a new replacement and try it again. And as you can see, the engine roars back to life after what might have been 50 years of silence. However, there is an issue. As soon as I take my hand off the gas lever, the engine stops. The mechanical regulator or governor that is supposed to keep the rotational speed constant is malfunctioning. We will take it off. disassemble it and see if we can get it working again. But before we do that, let us measure the output voltages of the electric generator. At variable speeds, we get 10 to 15 volts DC open circuit and 550 to over 600 volts DC open circuit respectively from the low voltage and high voltage outputs. Under load and when the regulator actually works, you will have 6.5 volts and 500 volts DC. These voltages are needed to power the vacuum tubes, and these measurements look very good. But we have to get that governor running again. And while we're at it, we will take off a bunch of other parts. That way we can check for possible issues and learn more about how the generator works. In order to disassemble this device, it might make sense to check the tools and additional equipment that came with it first. They even included replacement parts for typical faults: gaskets, fuses, motor brushes, the plastic covers to screw in the brushes, another spark plug, and so on. Before actually opening the speed regulator, let's remove a few other parts. I start with the gas tank and carburetor, and I remove them together since they are still connected with a fuel hose. Inserted into the fuel inlet of the carburetor, we find this really dirty fuel sieve here, apparently made from brass wire, and we should clean that. The carb itself looks clean. We also open the enclosure housing the electronic circuits of the generator. We have to do that to be able to detach this enclosure from the generator altogether. Inside we find capacitors, some chunky resistors, and some chokes. All these parts comprise RC and LC filters to smooth out the output voltages, which would be very important when powering a radio transceiver with it. While we're at it, we also clean the surfaces. And here is a closer look at one of the generators of one of the 6 units, as we need to look at all of the units to make sure they all work. Basically, these are 2 generators coupled together, one providing 6.5 volts DC to heat the vacuum tube filaments and power the field coil of the generator, and one 500 volt DC generator for the transmitter tubes. The low and high voltage generators have their own commutators, and the wires are marked high voltage and low voltage here as well. These are capacitors and one power resistor fastened inside the enclosure of the generator. They wanted to make sure to have these filter components as close to the source as possible. By the way, isn't it just amazing to see 65-year-old components that look almost like new? In the next step, we will detach the governor from the housing of the engine. Removing the cover on one side allows you to take a look inside and see how much oil is still inside the governor's housing. But if you really want to understand what's going on here, you have to take off the entire assembly. This axle here directly connects to the motor shaft, as we can see in this drawing here. Under this side cover, we can see how this push rod that connects to the carburetor is coupled to the inside of the governor. Upon pulling out the axle, we can see that this actually is a kind of centrifugal governor. As the motor shaft rotates, the weights are pushed away from the center of the rotation, pulling out this pin, which then moves the rod that connects to the carburetor. As the electric load on the generator increases, the engine's rotational speed decreases. The weights move closer to the center, moving the peg, adjusting the gas lever so that the engine spins faster again. This ensures that the generator can work with varying loads, keeping the output voltage stable. In an AC generator, it would also ensure that the AC's frequency doesn't drop too low. The governor can be adjusted, but I'm pretty sure that all we need to do here is to oil it and move its parts around after sitting for 50 years. And that is exactly what I did here. I also filled the housing with new oil. The governor has now a completely different feel to it. It feels springy and seems to move freely, as it should. So let's try it again then. And as you can see, the engine can now run by itself without the need for human assistance. So what are we going to do with 6 of these super specialized generators built for radio equipment that I don't have and that I'm not planning to operate? Well, I have decided to keep 4 units as they are. Before I bought them, nobody wanted them, but I will keep them in storage for the time being. But I will use the 2 remaining units to experiment a little bit and see if we can convert these units into something more useful. Our first experiment will revolve around the question if it will be possible to squeeze more power out of these generators than what they were originally built for. These engines are able to generate 1 to 1.2 metric horsepower of mechanical output. That's somewhere between 700 and 900 watts mechanical. Even an electric generator that works with only 70% efficiency should be able to get 400 to 600 watts of electric power out of this engine. The old electric generators are only rated for 150 watts though. I'm pretty sure that the German military built these units so that they would be super reliable and long-lived, while delivering a smooth output voltage at a power level way beyond what you could squeeze out of the material. But I want to see if I can at least generate 400 watts of electric power here. For that experiment, we are going to connect this brushed DC motor to the Sachs engine. It's a treadmill motor that we found on a scrapyard some time ago. It was featured in one of the earlier Repair-A-Thon episodes. All older episodes are listed in the video description under this video, by the way. The first thing that I did was to design in 3D print this connector piece here that will allow us to connect the engine shaft to our new DC generator. In the next step, I'm removing some of the old paint, so that in the next step, some new steel pieces can be welded to the old frame. This was necessary so that both engine and DC motor can be bolted to that frame. It would be better to use shock absorbers instead of bolts, but I simply don't have any fitting shocks here right now. And this is the experimental setup. The left DMM measures the output current and the right one the output voltage. As a load, we will use this adjustable dummy load we built in an earlier episode. The bulbs were built for 230 volts, while the generator will put out more like 100 to 120 volts DC. If I had 120 volt bulbs here, I would screw them in instead. So don't be surprised that the bulbs won't light up very brightly. But it doesn't matter, since we have the multimeter set up. You should focus on the measurements rather than on the brightness of the bulbs. The supply voltage drops as the load increases. This not only depends on the engine's RPMs, but also on the internal resistance of the DC motor, which is used as a generator here. Old-fashioned generators, like the one in the bigger unit we will work on in just a few minutes, have a field coil instead of permanent magnets, which will allow you to counteract that effect. On the other hand, this permanent magnet motor probably works with a higher efficiency. The voltage could be stabilized with a DC to DC converter, though. But we're not going to perfect the setup in this video. I simply wanted to prove that it is possible to get more electric power out of it. Another idea that I had for these engines originated in the fact that last summer parts of Germany were flooded because of extreme rainfalls. In this street here, it happened twice in 3 weeks. The feeling of helplessness was tremendous, as many people waited for days until the firefighters could come to pump out the basements. Instead of using electric energy in an environment like this at all, it might be smart to run a pump directly on a small combustion engine. This pump here was another scrapyard find, and you guessed it, it was also repaired in an earlier episode. So another steel frame was built and welded together, and as luck would have it, no connector piece was even necessary, as the pump simply fit the engine. So I connected some hoses here, and we'll just try to pump some water out of this tub here and put it back in. I'm pretty happy with both results here, but I could also imagine that I will try to build my own electric generators to be connected to these engines here in the future. It is time now though to take care of the bigger unit. This is a 750 watt generator, but this time for 220 volts AC. In other words, for normal mains powered equipment as it is used here in Germany. Like the smaller units, this device was built by Eisenmann, using a Sachs stationary motor. The engines in the smaller units are Sachs ST50s, which have close to 50 cubic centimeters of displacement, while this is a Sachs ST100 with roughly twice that displacement. Other than that, this engine is almost identical to the smaller ones. Unlike the smaller units though, it looks very dirty. It has a volt and ammeter and a frequency meter for 50 and 60 Hz and also a variac for voltage adjustment. Despite its grimy appearance, at least according to the counter, it has only seen 40 hours of work. According to this additional nameplate, the generator was overhauled in 1979. Überholt durch Heeresinstandsetzungswerk 800, Materialerhaltungsstufe 4. Overhauled at Army Maintenance Works 800, Material Conservation Level 4. That maintenance facility still exists, but is now referred to as a Center for Mechatronics. The conservation levels go from 1 to 4 or 5. Simple maintenance tasks of levels 1 and 2 are supposed to be performed by the user on a regular basis. Level 4 would describe much more complicated repairs or modification jobs of the unit. The simpler tasks are explained in this Army manual here that I bought to learn more about this device. The manual alone cost me 100 euros, as they are really hard to get now. It describes some of the features of the generator and its predecessor. It doesn't deliver any detailed information about the engine and no proper explanation of the electronic circuits though. Let's say these books were designed for a need-to-know basis and to be used by troops in the field. It would have been nice to have access to the technical documentation they certainly used at the facility back in '79, because, as always, I had to figure out a lot of stuff here all by myself. German two-stroke engine sitting for 30 years. Will it run? Yes, it just does. But let's see if we can actually generate any power here. Well, this isn't good. The voltmeter shows no voltage. Yet the engine clearly works on a significant load here, and the ammeter is showing readings way beyond the rated current. In other words, I needed to turn this unit off ASAP. Looks like the generator was working, but there was a short circuit inside the unit. That's not good at all. In the next step, we need to open the enclosure and find the fault. After detaching the wires, connecting the actual generator to this enclosure, we can remove it from the unit. On the back side of the front panel, we see the variac for the fine adjustment of the output voltage, a circuit breaker, and of course the various meters. After unscrewing a lot of very inaccessible screws, I managed to pull the actual circuits out of the enclosure. What happens within seconds in this video often takes hours in real life, by the way. Just figuring out how to disassemble something like this can take forever. Keep in mind, you have to mark or remember every connection you remove to be able to put everything back together later. The actual regulator that controls the field current and keeps the output voltage stable works with passive components only. 3 transformers or chokes with various tabs each working in conjunction. Understanding this properly without documentation is quite the challenge, if I may say so. But we're going to have a closer look at that later. First, let's keep an eye out for obvious damage. If we just measure the resistance between the 2 contacts of this outlet, we detect a direct short circuit here. Looking at it from behind, we see an old filter. In the rough circuit diagram on the backside of the cover, which is the same as the one in the manual, that would be this part here. It appears to be an ordinary line filter, as you can also find it in household equipment and power tools. We just remove it entirely for now, as the generator should be able to function without that. I also took a closer look at the actual generator itself. From the outside it looks very similar to the generator in the smaller units, but it's actually quite different. While the 150 watt DC units had 2 generators with 2 commutators, the 750 watt AC unit has no auxiliary DC generator to power the field coils at all. It has 3 slip rings for single-phase AC. Actually, you would only need 2. The third connection is for 60 Hz output. The unit was built so that it could be used for either 50 or 60 Hz equipment. The brushes and rings look okay though. Since I didn't see any other urgent problems at that time, I put the unit back together. I put some extensions between the generator and the electronics. I did that so that I would be able to work on the electronics again without having to disassemble everything all over again. So it was time for a second test. There was no longer a short circuit, alright, but now we simply didn't get any output current at all. Under a direct short circuit, the generator worked, but with a much smaller load, the generator doesn't produce any meaningful output voltage. And I really tried to wire everything up correctly here, and I tried over and over again, but after 2 weeks off and on, trying again, I almost lost hope that I would be able to get this machine running at all. The problem is clearly with the complicated regulator that is supposed to feed the field coil of the generator though. Remember, this type of generator has no permanent magnets. Instead, a magnetic field has to be generated by supplying a voltage to the field coil first. When there is no current flowing through the field coils, the external magnetic field is way too weak for a meaningful amount of voltage to be induced in the rotor and to be tapped into via the slip rings. However, there is a residual magnetic field even when no current is flowing. The term here is remanence. The remanence of the stator would allow this regulator to build up a field current until the generator works at the rated output voltage. And that regulator needs to be repaired. With no proper circuit diagram, I really wasn't looking forward to this though. I wasn't sure if I would be able to repair it at all. But then I had an idea. Before we try to figure out the circuit, let's see if the coils even still work at all. So I connected a lab power supply to the field coil to see if the rotor would deliver 220 volts if I could just feed a small direct current through the field coil at just a few volts. And as you can see, the 230 volt light bulb lights up. The lab power supply struggles and fails because it can't deliver the current required, but this proves that the field coil still works in principle. I had won back some hope and was ready to go to work. I sat down and traced out all the connections of the strange old regulator and came up with a circuit diagram. Now, there is still the problem that the circuit diagram only shows what I found, not necessarily what's supposed to be there. Remember, nobody knows how many other people have mucked around with this before. Some connections might be wrong in the first place. However, I felt ready to tackle this issue again. But then the Zax engine wouldn't start anymore. Now the electronics were down and the engine was malfunctioning as well. I felt really annoyed, and it wasn't just back to square one. In fact, I was worse off than before I had started. It took some time for me to regroup and tackle the issue once again. First task, get the engine back running. So I figured maybe it's time for a general overhaul. I detached the engine from the generator and started to take as many of the attachments off as I could. The housing was cleaned, even the fan guard. The carburetor was taken off and disassembled into all its components. After that, the parts were put into the ultrasonic cleaner. The muffler was detached and taken apart. This is necessary because the oil in the two-stroke mixture leads to a kind of coal deposit inside the silencer. These deposits have to be burned out. According to the manual, the strange old air filter is supposed to be washed in gasoline, and after cleaning and drying it, it's oiled, probably to prevent corrosion. And while I was at it, I decided to clean the grime and dirt off the steel frame as well. The carburetor and the engine as a whole were reassembled. Once again, what happened here in minutes took days to accomplish. And believe me, I was really hoping that it would run once again. And now we're back in business. Okay, so the motor is running, and we had already shown that the field coil works in principle. Maybe some of the parts here were either not wired correctly or faulty. In the meantime, I had enough time to think about it, and here is what we're going to do. We're going to reduce the regulator to its most basic function. Let me explain what we even have here. We have one AC generator with a field coil and 3 brushes for 2 different frequencies. We have one capacitor, an adjustable resistor, and a choke with one tap. We have a transformer with 10 different connections and 2 windings. We also have an auto transformer with 1 tap, as well as a variac with an additional center tap. Also, last but not least, a full bridge rectifier. Let's see how we can simplify the circuit then. This entire branch of components is connected to the 60 Hz slip ring / brush, and we will probably never need that in our entire life since this is a 50 Hz country. Let's just disconnect them. The switch can go as well, since its only purpose is to switch between 50 and 60 Hz. The variac and the auto transformer are connected together in a rather weird way, and it might well be that they are not connected correctly. I believe that their purpose is simply to do fine adjustments to the output, and if anything would be wrong there, we can just wire them differently or just use another variac. Let's remove them as well and just connect a 220 volt load directly here. All these tabs are now not in use, so just ignore them. All we have left is 1 transformer and a full bridge rectifier, and it's pretty clear what happens here. The transformer's primary is connected in series with the load. When the load increases, the voltage induced in the secondary is also increasing. That AC voltage is rectified by the rectifier and fed into the field coil. In other words, connect a big enough electric load, get the engine started, then the residual magnetism should supply the primary with a voltage, the secondary supplies the field coil, and this should start a positive feedback loop until the generator works at full power. Yes! Yes! That's what I'm talking about. Okay, so just for clarification, I left all those components physically attached to that assembly, but everything but that transformer is electrically disconnected. You can also see a fuel tank that I had built in the meanwhile. The basic problems of the generator are all solved. The remaining issues like rewiring the variac and the auto transformer are very simple compared to everything else we have done here. Some of the generators will return in the next episode though. And here are some final words. If there's one crime that I'm guilty of, and that I'm willing to admit publicly, is that I have made my work look too easy in the past. Even though I have gotten rather efficient at my repairs, nothing here is ever easy, and especially the younger viewers should know that. And frankly, I don't know how many hours went into this video, but I'm pretty sure that it could be more than 150, since I'm trying to share my own struggles and lessons learned here free of charge, even though they have been acquired with blood, sweat, tears. I'd say that it's only fair if some of you who can't afford it would donate a few bucks to the channel. Link for that under the video. Or become a supporter on Patreon under patreon.com/tpai. See you soon.